What we want to talk about now is calculating equilibrium concentrations when a common ion is involved. Now, a common ion is just an ion that both the weak acid and the weak base have in common. And in fact, the weak base is the common ion. So here we have hydrogen fluoride and we have fluoride ion. If I had, let's say, a 0.50 molar concentration of hydrogen fluoride and a 0.25 molar concentration of fluoride ion, that is actually going to change the percent ionization of the hydrogen fluoride in solution. You can look at this with respect to Le Chatelier's principle, because hydrogen fluoride, hydrofluoric acid, is our reactant, and fluoride ion is a product of the ionization of hydrogen fluoride in water. And if we look at it that way, the presence of a substantial amount of fluoride ion in that same solution will reduce the percent ionization of the hydrogen fluoride in solution. I can prove that to you mathematically by, let's say, just taking hydrogen fluoride by itself without putting any additional fluoride ion in solution. So let's say we've got a solution of weak acid, hydrogen fluoride. We're going to go ahead and use an ice table as we have done before. And let's say our concentration of hydrogen fluoride by itself is 0.500 molar. We have no hydrogen ion and no fluoride ion to start our problem. The change will be minus x, and plus x. And then at equilibrium, we'll have 0.50 minus x, and then just x. Again, we're calculating primarily the percent ionization of the hydrogen fluoride, the weak acid by itself. So just weak acid alone. And we're doing this just to contrast it to calculating the percent ionization of hydrogen fluoride with a substantial amount of its common ion, fluoride ion, in solution. So we'll write the Ka expression for our weak acid, which is just going to be H plus times F minus divided by the HF concentration. All right, so now we're going to go ahead and just plug in the values. The Ka for hydrofluoric acid is 6.8. 6.8 times 10 to the minus 4. X times x are our two products, which is just x squared. We're going to go ahead and assume this x is small. We'll calculate the percent ionization just to make sure we were valid in our assumption. And we have divided by 0.50. X, which is going to equal the hydrogen ion concentration, is just equal to the square root of 6.8 times 10 to the minus 4, and we need to multiply that times 0.50. We get an x that's equal to 1.84 times 10 to the minus 2. 1.84 times 10 to the minus 2. If we calculate the percent ionization, that's going to equal 1.84 times 10 to the minus 2 divided by our original or initial concentration, 0.50 times 100. And when I do that calculation, I get a percent ionization of 3.7%. So that's just the percent ionization of the weak acid by itself without any additional fluoride ion in solution. Now we're going to change the problem and we're going to recalculate the percent ionization. Only this time what we're doing is we're taking some sodium fluoride, which is a basic salt. It's a salt of the conjugate base of hydrofluoric acid. So we'll put 0.25 moles per liter in solution in water. We'll get 0.25 moles of the sodium cation and 0.25 moles of the fluoride anion. We know that the sodium cation is neutral. It doesn't affect anything, but the 0.25 molar solution of fluoride ion is going to change the percent ionization and effectively change the pH as well. So we'll go ahead and we'll calculate. This will be the initial concentration. The change will be minus X plus X, because initially we had 0 hydrogen ion, plus X plus X, and then at equilibrium we'll have 0.50 minus X, X, and then just 0.25 plus X. Again, we're going to write the equilibrium constant expression, which is Ka is equal to H plus times F minus and divided by our HF concentration. Now we'll plug in our values. We've got a Ka of 6.8 times 10 to the minus 4 is equal, only this time, and by the way, we are also considering X as small for both of these values. We'll again calculate the percent ionization to make sure, but this is going to be from the ICE table X times 0.25 divided by our initial concentration of our weak acid, 0.50. If we do the math on that, we calculate the value of X, which is equal to 6.8 times 10 to the minus 4 times 0.50 times 0.50 divided by 0.25. And when we calculate X for this calculation, we wind up with 1.36 times 10 to the minus 3. We'll go ahead and calculate the percent ionization, which is equal to 1.36 times 10 to the minus 3 divided by 0.5 and times 100. And when we do that, we get a percent ionization that is equal to 0.272%. So as you can see, when there is a common ion, the conjugate base, that's going to be the common ion, the conjugate base of the weak acid, the percent ionization goes way down. This is based on Le Chatelier's principle that says if we add product, the reaction has an equilibrium shift in this direction. This is a phenomenon we're going to use in the next section when we talk about buffers.